Hello friends, hi Dr. Manil Verma, welcome you all in this course on the fundamental of engineering physics, and today's topic, that is the photoelectric effect and its equation derivation. So, the outline of this lecture, that is we will start with the terms electron emission, because that this effect is basically based on that emission of electrons. So, we will begin with this electron emission, and then we will move to the main concept, that is the concept of photoelectric effect, it is a definition, and then experimental setup for the analysis of different properties of this photoelectric effect, and then the properties of photoelectric effect we will list out and discuss about that, and then we will try to explain this the behavior of this photoelectric effect on the basis of that classical wave theory, and we will discuss how this theory fails, and it is finally explained on the basis of that quantum theory of light, and that explanation was done by this Einstein's equation. So, we will conclude this with this Einstein's equation. So, the objective of this lecture, so the main objective is to introduce the concept of emission of electrons and photoelectric effect, and the important knowledge on quantum theory of light, and to introduce experimental evidence of photoelectric effect, and also to discuss about Einstein's theory to explain photoelectric effect. After going through this lecture, you will be able to understand the basic concept of quantum theory of light and the properties of photon to explain this photoelectric effect, and apply the quantum theory to understand photoelectric effect and related properties, and learn some more fundamental mathematical formula to solve different properties related to that photoelectric effect in the quantum level. So, the introduction or the background of this. So, this is related to two terms, one is that photon, and then the conversion of that photon into electrical, because that name is that photoelectric. So, we should start with that the light, because that is in the background. So, we know about this light, it is a special one, because without light even we cannot see the object, and this is the term light, which actually puzzle made to many physicists sleepless until middle of 19th century. So, it is really a mysterious phenomena, the propagation of light in vacuum or in the medium, and it is the only because of its abundant properties, and we have listed out so many properties in the one of the lecture related to the introduction of this quantum theory, and also mention that there are certain special phenomena like black body radiation, Compton effect, photoelectric effect, and this cannot be these are that listed in that property, and that classical physics is not adequate to explain these properties. So, in 1887 this Hertz noticed that in his experiment on electromagnetic waves, that is sparks occurs more readily in the air gap of the his transmitter when ultraviolet light was discrete at one of the metal balls. So, this that experimental setup, there was that metal ball, and this was that the experimental during the generation of this EM waves, and he did not follow up the complete observation, but other did, and they discovered that the cause was electrons emitted when the frequency of light was sufficiently high. This phenomena is known as the photoelectric effect, and the emitted electrons are called photoelectrons. And in metals, even at room temperature, there are large numbers of free electrons which are moving inside the metals in random manners, and these are so free that generally we consider this as electron gas, but they cannot leave the surface of the metal, because when free electrons reach the surface of the metal, they are attracted by the positive nuclei of the metal, and the potential barrier which prevent these free electrons from leaving the metallic surface is called the surface barrier. And this free electron possesses some kinetic energy, but this energy is not sufficient to overcome that surface barrier, and whenever some additional energy is given to the free electrons, they will have sufficient energy to cross the surface barrier and they can escape from the metallic surface. And the liberation of this electron from any surface of any substance, especially on metal, it is known as electron emission. So, that electron emission, this is emission of that electron from the surface of that metal when we provide extra energy to break that barrier to electrons. And there is one term that is given special attention to this photoelectric effect, that was actually the work function. So, this is that work function which is actually the minimum energy needed for an electron to escape from the metal surface is called the work function of the metal. So, what we have, initially it has some kinetic energy, but it is not sufficient to break that surface barrier to come out that electron from the metal surface, and there is a need of that minimum energy to provide that electron to break that barrier, and that minimum energy is known as that work function, and this work function is in general denoted by phi naught, and it is measured in electron volt. And the actually this work function is the different for different metals. For different metals it is different, and it is a typical properties of metal. So, one can say this is one of the characteristic property of metal, and the nature of their and also that nature of that surface of that metal. So, let the maximum kinetic energy of free electrons, for example, inside that metal is, for example, let us take this is by 0.5 electron volt, and the energy needed to overcome that surface barrier of an metal is 3 electron volt. So, that barrier energy of that metal it is 3 electron volt. So, that energy what actually this electron is having, it is 0.5, but it needs 3 electron volts, then the minimum energy required for electron emission from the metallic surface will be obviously the difference of these two, and that is 3 minus 0.5, it is equivalent to 2.5 electron volt. So, here this 2.5 electron volt, this is the minimum energy required to give that electron to come out from that metal surface, and this is known as the work function. So, the material with his smaller work function it is more effective in electron emission. So, if we want to use that material for electron emission, then we generally choose that material having a smaller work function. So, the metal selected for electron emission should have low work function, and the electron emission is categorized into different types depending on the form of energy being utilized. So, we have different methods to give that energy to that system. So, the first one is that is the thermoionic emission. So, these are some electronic emission terms, and these are depending on that methodology we have classified. Thermoionic emission, when a metal is heated to a high temperature, the free electrons on the surface of that metal get sufficient thermal energy, so that they are emitted from the metallic surface, and this is known as thermoionic emission. Means that energy we are trying to provide that electron, it is in the thermal form, in form of temperature, and that intensity of thermoionic emission, this only depends on the metal used and its temperature. And the examples of thermoionic emissions are the cathode ray tube, electron microscope, and X-ray tubes, etc. So, that in that Coolidge tube that thermoionic emission properties are used to radiate that electron from filament. Now, the field emission. So, the electric field emission occurs when one very strong electric field is applied across the metal. This strong field pulls the free electrons and helps them to overcome the surface barrier of the method. So, the main mechanism is just we have to break that surface barrier to provide that energy up to the that work function, equivalent to that work function. So, here that we are providing that energy in form of electric field emission. So, that is this type of emission is known as field emission. An example of this field emission, it is a field emission is scanning electron microscope, FESEM, and field emission display. So, these are that examples of this emission. And then now the photoelectric emission, when electromagnetic radiation, that is in form of photons of suitable frequencies incident on the surface of the metal, the energy is transformed from the radiation to the free electrons, hence the free electrons get sufficient energy to cross the surface barrier and the photoelectric emission takes place. So, this is the third type of emission, that is known as photoelectric emission, and here the numbers of electron actually emitted, it depends on the intensity of incident radiation. Examples are photodiode and photoelectric cells. Now, the secondary emission, when a beam of fast moving electrons strike the surface of the metal, the kinetic energy of the striking electron is transformed to the free electrons on the metal surface. Thus, the free electrons get sufficient kinetic energy, so that the secondary emission of electrons occurs. And the examples are that image intensifier, photomultiplier tubes, these are that examples of secondary emission. So, here that energy is given by the striking of that electrons itself. So, that is why this is known as secondary emission. Now, the photoelectric effect. So, initially in the background section we have discussed about this Hertz observation. So, here I am giving little bit the details of that Hertz observation to understand this photoelectric effect in depth. So, the Maxwell's theory predicted the existence of electromagnetic wave and concluded that light itself is just one electromagnetic wave, and that experimentalist tries to generate this detect electromagnetic wave through various experiments. In 1887, Heinrich Hertz was successful in generating the and detecting electromagnetic wave with high voltage induction coil casing one spark discharge between two metallic spheres. When a spark is formed, the charges will oscillate back and forth rapidly and the electromagnetic waves are produced. So, these are that methodology of generation of that electromagnetic wave. So, this EMF electromagnetic wave produced were detected by the detectors that has the copper wire bent in the shape of that circle, and it was noted that the smaller detector spark became more vigorous when it was exposed to ultraviolet light, and the reason is of this was not known at that time. And later it was found that it is due to the photoelectric emission, and whenever ultraviolet light is incident on the metallic sphere, the electrons on the outer surface are emitted, which caused actually the spark to the more vigorous. So, the injection of electrons from the metal plate when illuminated by light in the suitable wavelength or the frequency, this is called as photoelectric effect. And these electrons, these are called that photoelectrons obviously, and the corresponding current, since it is related to photo, so that is known as photocurrent. And if we think about that material, then that material having this photoelectric effect is known as photosensitive materials. And we have some examples. So, metals like cadmium, zinc, magnesium, these are showing photoelectric emission with ultraviolet light, whereas some alkali metals like lithium, sodium, cesium, this responds well even to the visible light. So, this is the experimental setup to understand this photoelectric effect phenomena in detail. So, this actually contains S is a source of electromagnetic waves, obviously that light and of known and somewhere that variable frequency is new and that intensity. So, the that source have the variables like frequency and intensity. And C is the cathode. Cathode means it is a negative potential made up of photosensitive materials, because it has to emit that electron. So, it must be one good photosensitive material. And the anode A, this collects that electrons, this is a positive electrode, and that electrons which are actually emitted by cathode. And there is a potential difference between this cathode and anode, it is provided by battery B, and there is that the plate A, this can be maintained as the desired positive or negative potential with respect to C. So, we can change that polarity of battery and we can change that the potential of this plate A. So, if observation is, if there is no light falling on the cathode C, no photo electrons are emitted. When ultraviolet or visible light is allowed to fall on cathode, then the photo electrons are liberated and it is attracted towards that anode, because some potential are maintained in between this anode and cathode. As in turn, photoelectric current is set off in the circuit, which is measured using that micrometer shown in that figure, and this the photocurrent, this can be measured as a function of these variables. First, the intensity of light, the potential difference between that electrodes we are maintaining, and also the nature of materials. So, it also depends on, and the frequency of incident light. So, the first variable let us take, that is the variation of this photocurrent with the intensity of light. So, in order to observe this effect on this photoelectric current as a function of intensity, we fix that frequency of the light and the accelerating potential between that anode and cathode, and this intensity is variation. So, we are taking this observation for different intensity, and the observation is that this photocurrent is actually directly proportional to intensity. So, here this figure shows the same. And then the second one is that the effect of potential difference on the photocurrent. So, the frequency and intensity, in this case that we pick that we have three variables, that frequency, intensity and potential difference. So, for observation related to the effect of one particular variable, we have to fix other two variables. So, here we will fix that frequency, intensity of incident light, and then initially the potential of A is kept positive with respect to C, and the cathode is irradiated with that given light, and this potential of A is increased and the photocurrent is noted, because this variable is there here, this potential. So, we increase that potential successively and observe that photocurrent. As the potential of A is increased, photocurrent also increases up to a certain stage, and where the photocurrent reaches saturation value, and this is represented by the flat portion of that graph. So, for different constant intensity, we can have different variation of that photocurrent with that potential, and for each intensity we have a different plateau region observing in this diagram. Next one is the concept of this stopping potential. This is also one of the basic terminology used in this photoelectric effect, that is stopping potential. So, what happened when we reverse this potential? When that negative potential is applied to A with respect to C, means we are just reversing that potential. So, suddenly that current does not immediately drop to 0. The kinetic energy of some of this photoelectrons, it is such that this can overcome the retarding electric potential and reach that electrode A, because that electrons are continuously moving towards that anode, and we suddenly reverse that potential, then it will not stop suddenly, because it has kinetic energy and it tries to overcome that the effect of that retarded electric potential. And when the retarding potential of A is gradually increasing, then that photocurrent starts to decreasing, and that photocurrent becomes 0 at a particular negative potential, and that is represented by V naught. So, this V naught is known as stopping potential. So, at the stopping potential, that most energic electrons is brought to rest, and therefore, that initial kinetic energy of this fastest electron. So, that kinetic energy we can represent that is equivalent to half mv square, and that V can be represented as V max, because it was moving with fastest speed, fastest velocity. So, this is V maximum. So, this the kinetic energy, it is balanced by that energy which is generated in the opposite direction with the potential. So, that is equivalent to E multiplied by V naught, and by just rearranging this formula we can calculate this V maxima, means that the maximum velocity of that electron, that is equivalent to root of 2 E V naught by m. And then the effect of frequency of light on stopping potential. So, here this the effect is shown in this diagram, and what we are observing here, that the greater the frequency of incident radiation, larger is the corresponding stopping potential. So, initially that in this figure we are observing that that we have different frequencies V1, V2, V3, and V3 is greater than V2, which which is also greater than V1. So, what we are observing? So, for that V1, that is stopping potential, it is less than that V2 and it is less than this V3. So, the frequency, greater the frequency, the stopping potential will be greater. Now, let us try to understand the laws of this photoelectric effect on the basis of that observation, that experimental observation. So, the first law, in a metallic surface, the emission of photoelectrons takes place only if the frequency of light is greater than a certain minimum frequency, and that minimum frequency is known as threshold frequency. For a frequency which is above this threshold value, the number of photoelectrons emitted, it is directly proportional to the intensity of light, and the saturation current is also directly proportional to the intensity of incident light. Now, the maximum kinetic energy of this photoelectron, this is independent of intensity of light, and also this maximum kinetic energy of the photoelectron, actually this is directly related to the frequency of incident of light. So, the kinetic energy, it is independent of intensity of light, but it is directly related with the frequency of that light. So, there is no time lag between incident of light and ejection of photoelectron. So, if we drop that light on that surface of metal, then that the emission of this photoelectron starts immediately. And once a photoelectric phenomena has been thoroughly examined through various experiments, then the attempt to explain this behavior, this was started with the on the basis of that wave theory. So, we have that wave theory, that classical theory, the Newtonian theory, and the failure of this classical theory, let us discuss. So, for the photoelectric emission, so that wave theory actually predicts that the maximum kinetic energy of the photoelectron, that is the K maxima, this depends on the intensity I of the incident light. This is according to that wave theory, that intensity, the energy, it is related to intensity of light. And this K maxima, this does not depends on the frequency of this incident light, this is according to wave theory. And the time interval between the incident of light and the ejection of electron, this is very long as per this classical wave theory. So, some standard assumptions this can be made when the light is incident on the given material on the basis of that classical wave theory. The light is absorbed in the top atomic layer of the metal, and for the given element, each metal absorbs an equal amount of energy, and the energy is proportional to the cross section area of A, and each atoms give this energy to one of the electrons. So, this is that basic assumptions related to that classical wave theory. Let us come to the main explanation of this photoelectric effect on the basis of that quantum theory of light, and we know about this quantum theory of light. Earlier we have also used that, and Max Planck in 1900 proposed the properties of that light on the basis of that that in small energy packets, and we know that small energy packets are not the ordinary one, it is just the vibrating packet, and the energy of that is that energy packet, it depends on its frequency. So, this E is equivalent to h nu, and this is that quantized one where this h is a Planck constant, and we have a group of different photons having different energy values, and this is quantized. And also we know that this light behaves both as wave as well as particles, it has dual nature, and we have proved light as a wave by calculating its velocity, energy, frequency, wavelength, and also we have proved this as the particle nature. So, that we have calculated this mass, momentum, energy, and velocity to prove that light has particle nature. And here in this photoelectric effect, we are going to use that particle nature of light. As I have mentioned that this double rule, that wave nature as well as particle nature could not be used at the same time. So, here we are using that particle nature of this light. So, there is Einstein's explanation. So, Einstein extended this Planck's quantum concepts to explain this photoelectric effect in 1905. Actually, here I would like to mention that whatever that experimental observation we have studied, that is given by Leonard and his students. So, that the value of this photocurrent as a function of intensity, frequency, that is stopping potential, potential in between that electrodes, these are that experimental observation by that, and that the photoelectric that the photonic theory of light, it was given by Max Planck, and that Einstein actually did that some smart work by just combining that experimental observation with this photoelectric with that photonic theory of light and explain that. So, this is known as Einstein's explanation of photoelectric effect. So, this explanation was done in 1905, and according to Einstein, this energy in the light is not spread over the wavefront, but is concentrated in small packets or energy quanta. So, this the packet that quantum nature of light they are doing, and therefore, light of frequency nu, this from any source can be considered as the stream of quanta, and the energy of each light quanta is given by E is equivalent to h nu. And when a photon of energy h nu is incident on a metal surface, it is completely absorbed by a single electron and the electron is ejected. Actually, here that one to one mapping type term is used by Einstein, that the one energy it is completely given to a single electron. There is no distribution of the energy to several electrons. No, one photon gives all of the energy to that electron. So, in this process this one part of energy, that photonic energy, it is used in overcoming that potential barrier of the metal surface, which is we know that the work function, and the remaining energy at the kinetic energy of the ejected electron from the so that energy value it is being completely used by that electron, and initially electron has some energy, and that work function the energy equivalent to that work function it absorbed from that photon, and then it tries to come over that the metal surface, and if it has still some energy remaining, then it gains kinetic energy. So, from conservation of that energy, we can say that the total energy of one photon, it is actually the sum of that work function plus the kinetic energy term. So, that kinetic energy of that electron is equivalent to half m v square. So, h nu is equivalent to work function phi naught plus half m v square. This is that equation which is known as Einstein's equation. And this explanation, if frequency is reduced, the kinetic energy of the photoelectron it is also reduced. At some frequency nu naught of radiation, the photoelectrons are just ejected with almost 0 kinetic energy. So, that is h nu naught, this is that minimum frequency where it is just coming out of that surface. So, this is equivalent to phi naught, and this phi naught is the work function. So, this is that schematic diagram of that Einstein's explanation. So, here that energy is the photonic energy is incident on that metal, and that energy is being used by electron. So, here we can modify that Einstein's equation is equivalent to h nu is equivalent to h nu naught plus half m v square. So, this is the final form of Einstein's equation. Now, the explanation. So, the experimentally observed fact of photoelectric effect, this can be explained with the help of Einstein photoelectric effect, Einstein photoelectric equation. As each incident photons liberates one electron, then the increase of intensity of light increase the numbers of electrons emitted, therefore increasing the photocurrent. Actually, in the as far as that quantum theory of light is concerned, that intensity of that photon, intensity of that light, it is not related with energy, it is actually related to the number of photons. So, the more number of photons are incident on the surface of metal, means more numbers of electrons are distributed, more numbers of photons. So, as in energy that intensity increases, means more electrons will be emitted due to more numbers of photons are incident going on the falling on that surface of metal. So, obviously, that will increase that photocurrent, and as the same has been experimentally observed, as intensity increases that photocurrent increases. Is equivalent to h nu minus that phi naught, where this phi naught is work function. So, if we rearrange in terms of this kinetic energy, so that it evidences that this k maximum is proportional to frequency, because this phi naught is constant. So, this kinetic energy, this will be proportional to frequency, and also we have observed the same. So, it is independent of intensity of light. There must be minimum energy which is actually equal to the work function of the metal for incident photons to liberate electrons from the metal surface, and below this value of the energy, emission of electrons is not possible, and correspondingly the exist minimum frequency, this called the threshold frequency, below which there is no photoelectric emission. This is also experimentally observed. And according to quantum concept, the transfer of photons energy to the electrons is instantaneous. So, there is no time lag between the incident of this light beam and that emission of that electron. So, this is just opposite to that whatever that classical theory was trying to show. So, this according to this theory, there is no time lag between the incident of photon and that emission of electron. This is one instantaneous type phenomena. So, as a summary, I would like to mention some points here. So, we have started that with that emission of electrons, and there are 4 types of that emission phenomena depending on that method of energy given. So, in order to the thing related to that photoelectric effect, that energy is given in form of light, in form of photons. Second thing, that there is the observation related to that photocurrent, which is because of that emission of electron from that metal surface with the effect of that light. We have 3 observations. First, related to that photocurrent as a function of intensity. As intensity increases, photo current increases. Second observation, that was related to the frequency. When we provide that energy up to a frequency which is greater than that threshold frequency, then that photo electron will emit, and as in turn we will get that photocurrent, and that is that frequency is known as the threshold frequency, that minimum frequency. And also we have the concept of that stopping potential. When we reverse that that potential in between that cathode and anode. So, that and we apply one fixed amount of the maximum amount of that potential to stop that electron to move and to control that kinetic energy, that is known as stopping potential. So, we have 3 parameters, that potential in between that electrodes, intensity as well as this frequency, and then we try to explain this with the help of that classical theory, but this classical theory fails because that it does not match with the observation. Then we have that quantum theory, where we use that energy light energy as a packet, and Einstein has used that quantum theory of light and given that equation, that E is equivalent to E is equivalent to h nu, and h nu that is equivalent to that work function plus the kinetic energy of that, and this kinetic energy is equivalent to E v naught. And further it was properly explained all the observation of that Leonard related to that photoelectric by this Einstein's equation as well as Einstein's explanation. Okay, so thank you all, enjoy learning.